Welcome to this video on LeetCode problem number 637, average of levels in binary tree. In this problem, we'll explore how to calculate the average value of nodes at each level of a binary tree, a common task in tree traversal algorithms. Let's dive into the problem and understand how to approach it step by step. The task is to compute the average value of nodes at each level of a binary tree and return these averages as an array. To calculate the average for a given level, you sum up all node values at that level and then divide by the number of nodes at that level. The input to the problem is the root of a binary tree, where each node contains an integer value and pointers to its left and right children, if they exist. The output will be a list of floating point numbers, where each number corresponds to the average value of the nodes at a specific level, starting from level 0. Let's look at an example to understand this better. In this binary tree, the root node has a value of 3, with two child nodes, 9 on the left and 20 on the right. The node with value 20 further has two children, 15 and 7. This structure creates 3 levels in total. For the given binary tree, the output is an array, 3.0, 14.5, 11.0. Here's the breakdown. At level 0, there is only one node with a value of 3, so the average is 3 divided by 1, which equals 3.0. At level 1, we have two nodes with values 9 and 20. Adding these gives 29, and dividing by two nodes results in an average of 14.5. Finally, at level 2, there are two nodes with values 15 and 7. Their sum is 22, and dividing by 2 gives an average of 11.0. Now consider another example. In this binary tree, the root has a value of 1, and it has two child nodes with values 2 and 3. This structure creates 2 levels. The output for this binary tree is 1.0, 2.5. At level 0, there is only the root node with a value of 1, so the average is 1.0. At level 1, the two child nodes have values 2 and 3. Their sum is 5, and dividing by 2 nodes gives an average of 2.5. Let's look at one more example. Here, the binary tree has a root node with a value of 4 and one child node with a value of 2. This creates 2 levels. The output is 4.0, 2.0. At level 0, there is only the root node with value 4, so the average is 4.0. At level 1, there is only one node with value 2, so the average is 2.0. These examples illustrate how the averages are calculated for each level. Now, let's consider the constraints and edge cases for this problem. The binary tree will have between 1 and 10,000 nodes, and the value of each node will be an integer within the range of -2,147,483,648 to 2,147,483,647. Importantly, the tree is guaranteed to be non-empty, so you don't need to handle cases where there is no root node. Some edge cases to think about include a tree with only one node, which means there is just one level, and its average is simply the value of the root. Another edge case is a tree where all nodes are aligned on one side, such as a left-skewed or right-skewed tree, which creates one node per level. Finally, you must ensure that floating point division is used to compute the averages accurately, especially for very large trees with up to 10,000 nodes or trees containing negative values. The problem we're addressing is to compute the average of node values at each level of a binary tree. To do this, we need to traverse the tree level by level, calculate the sum of the node values at each level, and divide that sum by the number of nodes at that level. The result is an array where each element corresponds to the average of a specific level. One approach we could consider is a recursive depth-first search, or DFS, which involves traversing the tree by its depth. In this method, we maintain separate lists to track the sum of values and the count of nodes for each level as we recurse. Once the traversal is complete, we compute the averages by dividing the sum at each level by the count of nodes at that level. While this approach has a time complexity of O(n), since each node is visited once, and a space complexity of O(h), where h is the tree's height, there are trade-offs to note. Managing multiple lists and performing post-processing to compute averages can make this method more cumbersome and less intuitive compared to other strategies. Now, let's explore a more optimized approach using breadth-first search, or BFS. This method processes the tree level by level, making it a natural fit for problems involving level-based computations. Here, we use a queue to traverse the tree, allowing us to handle one level at a time. At each level, we compute the sum of node values and the number of nodes directly while iterating through the queue. Once we have the sum and count, we calculate the average and append it to our result array. The BFS approach has a time complexity of O(n), as each node is visited once, and a space complexity of O(w), where W is the maximum width of the tree, representing the largest number of nodes at any level. This strategy is particularly intuitive for this problem since it processes levels sequentially, which aligns directly with the task. However, the memory usage depends on the tree's width, which could be significant for particularly wide trees. A key insight for this problem is that level-based traversal matches perfectly with the goal of computing level-wise averages. BFS, in particular, processes the tree level by level, which simplifies the task of performing level-based computations. The major realization, or aha moment, was that BFS enables us to compute sums and averages in a single traversal, reducing code complexity and runtime overhead. While DFS is a valid alternative, it requires post-processing to compute averages, which adds additional complexity. BFS, on the other hand, is more direct and intuitive for this problem. One trade-off to consider with BFS is its memory usage, as the queue can grow large for wide trees. However, it still strikes the best balance between clarity and efficiency. In summary, BFS is the optimal choice for this problem because it aligns directly with the requirements, ensuring efficient computation of level averages in a straightforward and concise manner. In this problem, the task is to calculate the average of the node values at each level of a binary tree. Since binary trees are hierarchical structures, we need to process nodes level by level. To achieve this, we use a breadth-first search, or BFS, which is ideal for level-order traversal. The input for this problem is a binary tree represented by its root node, and the output is a list of averages, with each average corresponding to a specific level of the tree. To solve this, we'll use a queue to manage the nodes during traversal and maintain a results list to store the averages. This ensures that we can process nodes systematically and calculate the required values efficiently. To begin, we initialize the queue by adding the root node along with its level, which starts at 0. For example, the queue might look like this: root 0. From there, we perform the BFS traversal. While the queue is not empty, we dequeue the current node and its level, add the node's value to the running sum for that level, and increment the count of nodes processed at that level. If the current node has children, we enqueue them along with their respective levels. Once all nodes at a particular level are processed, tracked easily using the level information, we calculate the average for that level by dividing the sum of node values by the count of nodes. This average is then appended to the results list. Finally, once all levels are processed, the results list containing the averages is returned as the output. The BFS approach is particularly well suited for this task because it processes nodes level by level, which aligns perfectly with our goal of calculating level-specific averages. A queue is critical here, as it ensures that nodes are processed in the exact order they appear in the tree. By associating each node with its level, we can systematically group nodes and calculate sums without needing additional data structures. This makes the algorithm both efficient and easy to implement. To summarize, the queue facilitates traversal, the results list stores the computed averages, and the running sum and count for each level ensure that averages are calculated without unnecessary overhead or extra memory usage. The results list is essential because it holds the final output, which is the list of averages for each level of the tree. After processing each level, the computed average is appended to this list. Additionally, maintaining running sums and counts for each level simplifies the calculation of averages, making the algorithm efficient. When analyzing complexity, the time complexity is O(n), where n is the total number of nodes in the tree, since each node is visited exactly once. The space complexity is O(w), where w is the maximum width of the tree, representing the largest number of nodes stored in the queue at any point during traversal. The algorithm also handles edge cases gracefully, such as returning an empty list for an empty tree, handling a single node tree correctly, and accommodating all tree shapes, including unbalanced ones, without any modifications. To illustrate the algorithm, consider the following binary tree. The root node is 3, with 2 children, 9 and 20. Node 20 has 2 additional children, 15 and 7. We start by initializing the queue with the root node and its level, so the queue looks like 3, 0, and the results list is empty. For level 0, we process the root node, 3. The sum for this level becomes 3, and the count of nodes is 1. We enqueue its children, nodes 9 and 20, along with their levels, so the queue becomes 9, 1, 20, 1. The average for level 0 is calculated as 3 divided by 1, which equals 3.0. This value is appended to the results list, so the results list now contains 3.0. At level 1, we process nodes 9 and 20. Their values are added together, resulting in a sum of 29, and the count of nodes is 2. We then enqueue their children. Node 9 has no children, but node 20 has 2 children, 15 and 7, so the queue becomes 15, 2, 7, 2. The average for this level is calculated as 29 divided by 2, which equals 14.5. This value is added to the results list, making it 3.0, 14.5. Finally, at level 2, we process nodes 15 and 7. Their sum is 22, and the count is 2. The average is 22 divided by 2, or 11.0, and this is appended to the results list. At this point, the queue is empty, and the final results list, 3.0, 14.5, 11.0, is returned as the output. The code solves the problem of calculating the average of node values at each level of a binary tree using a breadth-first search (BFS) approach. Here's how it works. 1. Imports and initialization. We import Deque from the collections module to efficiently manage the queue used in BFS. The function average of levels takes the root of the binary tree as input. 2. Base case. If the binary tree is empty, root is none, we return an empty list as there are no levels to compute. 3. Queue setup. We initialize a queue with the root node. The queue will help us process nodes level by level. 4. Processing levels. The while loop continues as long as there are nodes in the queue. For each level, we initialize level_sum to accumulate the sum of node values at the current level. The level_count stores the number of nodes at the current level, length of the queue. 5. Node processing. A for loop iterates over all nodes at the current level. We dequeue a node from the left of the queue and add its value to level_sum. If the node has a left child, it's added to the queue for the next level. Similarly, if the node has a right child, it's added to the queue. 6. Compute average. After processing all nodes at the current level, we compute the average by dividing level_sum by level_count and append it to the result list. 7. Return result. Once all levels are processed, we return the result list containing the averages of all levels. This implementation ensures that each node is visited once, making the time complexity O, n, where n is the number of nodes in the tree. The space complexity is O, m, where m is the maximum number of nodes at any level of the tree, due to the queue storage. Here, we start with the Java implementation of the solution. First, we import the necessary utilities, including list, ArrayList, and queue. The method average of levels takes the root of a binary tree as input and returns a list of doubles, where each double represents the average of node values at each level of the tree. We handle the edge case where the root is null by immediately returning an empty list. Next, we initialize an ArrayList to store the results and a queue to facilitate level order traversal of the tree. The root node is added to the queue to begin the process. Then, we enter a while loop that continues as long as there are nodes in the queue. Inside the loop, we calculate the number of nodes at the current level using queue.size, and initialize a variable level_sum to accumulate the sum of node values for this level. A for loop iterates through all nodes at the current level. For each node, we remove it from the queue, add its value to level_sum, and check if it has left or right children. If it does, those children are added to the queue for processing in the next iteration. After processing all nodes at the current level, we calculate the average by dividing level_sum by level count, then add this average to the result list. Once the while loop completes, meaning all levels of the tree have been processed, we return the result list containing the averages. At the end of the class, we define a nested static class treeNode, which represents a node in the binary tree. Each node has an integer value and 2 child references, left and right. A constructor initializes the value of the node when it is created. This implementation efficiently traverses the tree level by level using a queue, calculating the required averages in O, n, time, where n is the number of nodes in the tree. Here, we are solving the problem of finding the average of nodes values at each level in a binary tree. Let's start with example 1, where we have a simple binary tree. The input represents a tree with root value 3, and its children are 9 and 20. Node 20 further has two children, 15 and 7. First, we initialize an empty result list to store the averages and a queue containing only the root node. In level 1, the queue contains just the root node with value 3. We calculate the sum for this level, which is simply 3, as it's the only node. We then enqueue its children, 9 and 20, and add the calculated average, 3.0, to the result list. Moving to level 2, the queue now contains nodes 9 and 20. We initialize the sum for this level at 0 and calculate it by dequeuing and adding the values of these nodes. After processing node 9, the level sum becomes 9. Next, we process node 20, adding its value to the level sum, which now becomes 29. We then enqueue node 20's children, 15 and 7, and calculate the average for this level as 29 divided by the number of nodes, which is 2. This results in an average of 14.5, which is appended to the result list. Now, for level 3, the queue contains nodes 15 and 7. We start with a level sum of 0 and process these nodes one by one. Dequeuing node 15, we add its value to the level sum, which becomes 15. Then, we process node 7, bringing the level sum to 22. Since these nodes have no children, the queue becomes empty. The average for this level is 22 divided by 2, which is 11.0. This is appended to the result list. At this point, all levels have been processed, and the final result list is 3.0, 14.5, 11.0. Now, let's consider example 2, which is a binary tree with just a single node. The input specifies a tree with only the root node having a value of 7. We start by initializing an empty result list and a queue containing just the root node. In level 1, the queue contains only this single node with value 7. We initialize the level sum at 0 and process the node by dequeuing it and adding its value to the sum. The level sum becomes 7. Since this node has no children, the queue becomes empty. The average for this level is simply 7 divided by 1, which is 7.0. We append this value to the result list. As there are no further levels to process, the final output for this example is 7.0. Finally, let's look at example 3, which demonstrates an unbalanced binary tree. The root node has a value of 5, with children 3 and 8. Node 3 further has a left child with value 1. We start by initializing an empty result list and a queue containing only the root node. For level 1, the queue contains the root node with value 5. The level sum is initialized at 0, and after processing this node, the sum becomes 5. We enqueue its children, 3 and 8, and calculate the average as 5 divided by 1, resulting in 5.0, which is added to the result list. Moving to level 2, the queue contains nodes 3 and 8. We begin with a level sum of 0, and after processing node 3, the sum becomes 3. We enqueue its left child, 1. Then, we process node 8, bringing the level sum to 11. The average for this level is 11 divided by 2, which is 5.5. This is added to the result list. At level 3, the queue contains only node 1. Processing this node gives a level sum of 1, and since it has no children, the queue becomes empty. The average for this level is 1 divided by 1, which is 1.0. Adding this to the result list, we get the final output as 5.0, 5.5, 1.0. The time complexity of this solution is O, n, where n represents the total number of nodes in the binary tree. This is because the algorithm uses a breadth-first search, or BFS, approach that processes the tree level by level. During this traversal, each node is visited exactly once. When a node is dequeued and processed, its children are added to the queue if they exist. This means that every node is visited exactly one time, contributing to the O, n, time complexity. Additionally, the operations performed at each level, such as summing up the node values and enqueuing children, are constant time operations for each node. Since the total number of nodes across all levels is n, the total work done remains proportional to n. Combining these observations, we can conclude that the overall time complexity of this approach is O, n. The space complexity of this solution is O(m), where m represents the maximum number of nodes at any single level of the tree, also known as the maximum width of the tree. The primary factor contributing to this is the queue, which temporarily holds the nodes being processed at the current level. In the worst-case scenario, such as in a perfect binary tree, the queue will hold approximately n/2 nodes at the bottommost level, where n is the total number of nodes in the tree. This leads to an O(n) upper bound for the queue size. Additionally, the solution maintains a result list that stores the average value of each level. For a balanced binary tree, the height is O log n, meaning the result list will contain O log n entries. However, since the memory required for the queue is usually much larger than the memory for the result list, the overall space complexity is dominated by the queue and remains O(m). When comparing this optimized BFS approach to a potential naive or brute force method, we can see significant advantages. A naive approach might use a depth-first search, or DFS, to traverse the tree, collecting data about node values at each level. This would involve creating additional data structures to track nodes at each level, leading to higher space overhead. Furthermore, after the traversal, you would need to process the collected data to calculate level averages, which would add additional time complexity. In contrast, the BFS approach directly calculates the sum of node values at each level during traversal, avoiding the need for post-processing. By only storing nodes for the current level in the queue, the BFS approach also minimizes space usage. This makes the BFS method far more efficient in both time and space compared to a naive DFS solution. Analyzing the best, average, and worst cases for this algorithm provides additional insight. In the best case, the tree is highly unbalanced, resembling a linked list. Here, the maximum queue size is O(1), since only one node exists at each level, and the time complexity remains O(n), as we still visit each node once. In the average case, which occurs in a balanced binary tree, the queue size is proportional to the maximum width of the tree. For a balanced tree, this width is approximately n/2 at the bottommost level, leading to a space complexity of O(n). The time complexity remains O(n), since every node is still processed exactly once. Finally, the worst case occurs for a perfect binary tree, which is essentially the same as the average case in terms of this algorithm. The maximum width of the tree and the queue size in this scenario are both O(n), and the time complexity is still O(n), due to the single visit per node. Overall, the algorithm efficiently handles all cases with a time complexity of O(n) and a space complexity of O(m), where m is the maximum width of the tree. Here are some common mistakes to watch out for when solving this problem. First, always handle the edge case of an empty tree. If the root is null and you don't check for it, your code can crash with a runtime error. The correct approach in such cases is to immediately return an empty list. Next, be careful when implementing the traversal. Using depth-first search, or DFS, without tracking levels properly can make it difficult to group nodes correctly. A breadth-first search, or BFS, with a queue is usually the better choice for level-based computations because it naturally processes nodes level by level. Another potential pitfall is integer division in languages like Python 2 or Java, where dividing two integers might truncate the result to an integer. To ensure you get a precise average, always convert either the numerator or denominator to a floating point number before dividing. Additionally, floating point precision errors can become significant when working with very large numbers or deep trees, so take care to verify your results if you suspect inaccuracies. Finally, watch out for inefficiencies in your implementation. For example, repeatedly summing nodes for each level can result in unnecessary computations. Instead, use a queue to process the nodes efficiently in one pass, which is both faster and simpler to manage. Now, let's talk about some insights that are especially helpful in interviews. This problem is an excellent example of how breadth-first search can be applied to traverse trees level by level. Since BFS is such a fundamental algorithm, it's a good idea to practice it thoroughly, as it often appears in coding interviews. When discussing your solution, make sure to mention edge cases explicitly. These might include scenarios like an empty tree, a tree with only one node, or an imbalanced tree where one side is much taller than the other. Interviewers often appreciate when candidates demonstrate awareness of these corner cases. Additionally, if the input tree is very large, you should consider optimizing memory usage. For instance, you can discuss techniques like processing nodes in place or reusing data structures to reduce the memory footprint. Finally, be ready to talk about how your solution could be adapted for variations of the problem. For example, instead of calculating averages, you might modify the algorithm to compute sums, find the maximum value at each level, or gather other aggregate statistics. This kind of flexibility and adaptability can make a strong impression during an interview. Let's look at some related problems that can help you deepen your understanding of this concept. A great place to start is LeetCode 102, which focuses on binary tree level order traversal. This problem lays the groundwork for understanding how BFS can be used to traverse trees level by level. Another useful problem is LeetCode 107, which is similar to problem 102 but requires you to reverse the level order, giving you practice with slight variations on the same core algorithm. For a more challenging twist, consider LeetCode 1161, where the goal is to find the level of the binary tree with the maximum sum rather than computing averages. This problem tests your ability to adapt level-based traversal for different aggregate calculations. Lastly, LeetCode 429 takes the concept into the realm of n-ary trees, challenging you to extend your BFS approach to handle trees where nodes can have more than 2 children. Working through these problems will not only reinforce your BFS skills but also prepare you for a variety of tree traversal scenarios. Finally, let's explore some alternative approaches to solving this problem. The most common and intuitive method is breadth-first search, or BFS. Using a queue, you can traverse the tree level by level, summing the node values for each level and then calculating the averages. This approach is efficient, with a time complexity of O(n), where n is the total number of nodes. However, it does require additional space to store the queue, which can grow as large as the maximum width of the tree. Another approach is depth-first search, or DFS, which uses recursion to traverse the tree. By maintaining a helper function that tracks the level, you can accumulate sums and counts for each level. Once the traversal is complete, you can compute the averages. While DFS avoids using a queue, managing levels explicitly in recursion can be tricky and prone to errors. If the problem allows, you could also consider in-place modifications to the tree, such as temporarily attaching metadata to nodes to store level sums. This can reduce the need for extra data structures, though it risks altering the input tree. Lastly, for extremely large trees, you might explore parallel processing. By dividing the tree into subtrees and processing them concurrently, you could compute level averages more efficiently, though this would require additional complexity in implementation. Each of these methods has its trade-offs, so choose the one that best suits the problem constraints and requirements. In summary, this problem showcases the use of breadth-first traversal to calculate averages across tree levels. It emphasizes the importance of BFS for tree-related problems and managing traversal efficiently with queues. Thank you for joining, and be sure to like, subscribe, and stay tuned for more coding tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!